M. Victor Anthony Raj. He has pursued his bachelor's, master's, and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Tiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to DTH channel, lecture 4 in Astronomy and Astrophysics. This lecture is about measurements in astronomy. I am going to present this lecture in the following way: introduction about measurements, units used in astronomy, trigonometric parallax method used to measure the distance of different objects in the celestial body, coordinate systems used in astronomy, and finally summarizing the discussions we are going to have. Measuring the position of various celestial objects is an important one in astronomy because we are in Earth. If you look at the sky, many objects will appear in the sky during night time. At what distance those objects are, that's very important for an astronomer and scientist. Measuring the position of location of these objects will be made with respect to Earth. Both linear distance and angular positions are calculated using the data obtained from the measurements. To do this, different coordinate systems are used in astronomy. We will be discussing all these things in this lecture. Coming to the units of measurements used in astronomy, distances are measured in 3 different units: light year, astronomical unit, parallax second. These 3 units are used to measure the distance of different celestial objects. Coming to light year is the distance traveled by light in 1 year. Using the velocity of light, it is learnt that light will travel with a velocity of 3 into 10 power 8 meter per second. That is, in 1 second, light will travel 300,000 kilometers. In 1 second, if light travels 300,000 kilometers, means in 1 year, light travels a distance of 9 trillion kilometers. The sunlight takes about 8.3 minutes to reach Earth. This means that we always see the sun as it was about 8.3 minutes ago with respect to the formation of universe. Coming to other planets in our solar system, according to the distance of those planets in light year, we can say those planets are this much time ago, this much time closer. This is how light year is used to find the position of different objects in solar system and the age of different objects in the universe. The next closest star to us is about 4.3 light years away. That means that star is 4.3 years ago, was formed 4.3 years ago. So when we see this star today, we are actually seeing it as it was 4.3 years ago. This is the understanding of light year. So light year is the distance traveled by light in 1 year. In 1 year, it travels 9 trillion kilometers. Coming to the next unit used in astronomy to measure the distance is astronomical unit. One astronomical unit is the average distance between Earth and Sun. Earth revolves Sun in an elliptical orbit. Ellipse does not have one center. it has two center. So, the radius of the ellipse will not be equal. So, in this figure you can see the two position of Earth in its orbit around Sun. Aphelion, the farthest distance from Sun, and perihelion, the shortest distance from Sun. So that the distance of Earth from Sun is keep on varying. That's why astronomers and researchers have calculated the average distance between the Sun and the Earth. This average distance is considered as 1 astronomical unit. 1 astronomical unit is about 149 million kilometer. 1 astronomical unit is equal to approximately 149 million kilometer. This average value is obtained from the variation of Earth's distance from Sun from 147 million kilometer to 152 million kilometer. This is how Earth's position varies from Sun throughout its path around Sun. So, the measurement of an astronomical unit is just the Earth's average distance from Sun. This is how astronomical unit evolved to measure the distance of different celestial objects with respect to Earth. The next largest distance, largest quantity in astronomy is parsec, parallax arc second. That's the extension of this parsec. This 1 parsec is equal to 3.08 into 10 power 16 meter. This 1 parsec is the distance to a star that subtends an angle of 1 arc second at an arc length of 1 astronomical unit. This parsec unit is obtained from the concept of parallax method. You know, parallax means deviation in the position of object when it's viewed from two different position. Deviation in the position of object when it's observed from two different. You can do this parallax, you can examine this parallax by your own way. For that you have to keep your left eye closed and extend your finger there and look at that finger using your right eye. Now the finger will appear in one position. Next, look at the same finger with your right eye closed and left eye open. Now the position of the finger will be shifted. So this is a simple experiment to understand the parallax in your own way. In the same way, astronomers have observed different stars in the sky when the Earth is in different position in its orbit. So, the nearest star to the Sun, a small red dwarf named Proxima Centauri, is just over 1 parsecond from us. So, from this parallax concept, 1 parsecond is defined as the distance to a star that subtends an angle of 1 arc second at an arc length of 1 astronomical unit. The nearest galaxy, Andromeda galaxy, is nearly 800 kiloparsec away from us. This is how parsec is used in the measurement of astronomy. You can look at this figure. In this image, you can see the Earth two different position. When the Earth is at this position, that is in the month of June, the distant star is measured. When Earth moves to the opposite diagonal position, that is in the month of December, same star is observed in different position. Now this angle, using the trigonometric calculation, geometric drawing, you got an angle. This angle is the parallax angle. This angle is 1 parsec, 1 arc second. Then this distance should be 1 astronomical unit. Then this distance is called 1 parsec. This is what the definition of parsec says, that the distance to a star that subtends an angle of 1 arc second. So this is the distance to a star that subtends an angle of 1 arc second when the measurement of position of the star, separation of position of the star is 1 astronomical unit. This is how 1 parsec can be understood. Now coming to the comparison of these three distance units used in astronomy, 1 astronomical unit is the smallest distance, then 1 light year, then 1 parsec. 1 astronomical unit is equal to 1.5 into 10 power 11 meter. 1 light year is equal to 9.46 into 10 power 15 meter. 1 parsec is equal to 3.08 into 10 power 16 meter. So parsec is the largest distance unit in astronomy. This parsec is used to measure the nearest star in our galaxy, in the universe. As we have seen earlier, the nearest star is 4.3 million light years away. These are the things, units used in astronomy. Next, coming to the coordinate systems in astronomy, 4 different coordinates are used in the measurement of astronomy. Altitude azimuth coordinate system, which is abbreviated as alt azimuth coordinate system, equatorial coordinate system, ecliptic coordinate system, galactic coordinate system. These are the 4 coordinate systems used in astronomy to measure the position of different objects. In general physics, we will be using 2 coordinate system, rectilinear coordinate system or rectangular coordinate system, then spherical coordinate system. There are equations and formulae to convert rectangular coordinates into spherical coordinate into rectangular coordinate. Here in this altitude azimuth coordinate system, that spherical coordinate systems are used, spherical coordinates are used. To measure an object, to locate the position of an object in rectangular coordinate system, 3 coordinates are used, 3 coordinates are required, 3 numbers are required. Here in this altitude azimuth coordinate system, 2 numbers are required to locate the position of an object. Here the object is a star. So the 2 numbers which specify the position of a star X in this system are azimuth and the altitude. Azimuth and altitude. Here I have taken that azimuth as capital A and altitude as small a. Altitude means height, azimuth means the angle. Coming to the measurement of altitude of the star X, this altitude is measured in angle, measured along the vertical circle through X from the horizon at Y to X. You can understand this concept more clearly from this figure. So here you can see a sphere. This sphere is the celestial sphere. Celestial sphere is nothing but an imaginary sphere around Earth. Earth is kept in the center of that sphere, and all latitudes and longitudes are drawn in that sphere. In that celestial sphere, great circles are drawn. Great circles are circles nothing but which is drawn around the sphere, a big circle. This is the concept of great circle in celestial sphere. You can look at the yellow plane here. This yellow plane is the horizon in this figure. So here is the measurer. This guy measures a star X. To locate the position of the star, he is in need of 2 coordinates in altitude azimuth coordinate system. That 2 coordinates are altitude and the azimuth A. Capital A is the angle, altitude is also angle. Now the altitude of X is the angle measured along the vertical circle through X from the horizon at Y to X. So this is your Y and this is X. So this is that arc. This arc in the sphere, celestial sphere, subtends what angle? That is the angle A. Then often used alternative to altitude is the zenith distance. z of x indicated by zx. Clearly z is equal to 90 minus a. This is the zenith position. Zenith is nothing but a point just above the observer. Highest point just above the observer is zenith. From that zenith, how far the star is, that is zenith distance. That zenith distance is obtained by subtracting the altitude from 90 degree. So, if you add this z and a, it will come 90 degree. So, that this zenith distance is obtained by subtracting this altitude from 90. So, the altitude can also be represented in another way by zenith distance. The next one is azimuth. Azimuth is defined as the angle between the vertical through the north point and the vertical through the star at x. So, here in this celestial sphere, this is that north point. So, this is the vertical through north point. Then you have to see the vertical through the star. This is the vertical through the star. This is the vertical through the star. So, this angle is measured as azimuth of the star. So, to locate the position of a star in altitude azimuth coordinate system, altitude is small a and azimuth is capital A. Altitude is measured from 0 to 90 degree and the azimuth is measured from 0 to 360 degree. So, this definition applies to observer in both the northern hemisphere and southern hemisphere, but there are drawbacks in this altitude azimuth system. What is the drawback is if a star is measured from two different positions, its coordinate differs. This is the drawback of this altitude azimuth system. So, the main advantage and the advantage of this system is it indicates clearly how high a star is above the horizon and in what direction it can be found. The main disadvantage is it is a local coordinate system. So, two observers at different points on the earth's surface will measure different altitudes and azimuth for the same star at the same time. That is the main drawback in this alt azimuth system. In addition, a star's alt azimuth coordinates change with time as the celestial sphere appears to rotate as the earth rotates. Despite these problems, most of the modern astronomy research telescopes use these altitude azimuth mounts owing to their own low cost and great stability. This is the thing about altitude azimuth coordinate system. The next coordinate system used in astronomy is equatorial coordinate system. This is the preferred coordinate system to pinpoint objects on the celestial sphere. For all the coordinate systems, celestial sphere is an important one. As I told, the celestial sphere is an imaginary sphere imagined around Earth as the center. It's a sphere with infinite radius. Unlike the horizontal coordinate system, equatorial coordinate systems are independent of the observer's location and the time of the observation. This means that only one set of coordinates is required for each object and that the same coordinates can be used by observers in different locations and at different times. So, the equatorial coordinate system is basically the projection of the latitude and longitude coordinate system we use here on Earth onto the celestial sphere. So, equatorial coordinate system is a thing. In this image, you can look at the celestial sphere. This blue color thing is the celestial sphere. Then this is the equatorial plane of the Earth, which is also called the celestial equator. This is north celestial pole and this is south celestial pole. These parallels are all declination. These verticals are all right ascension. This latitude, then longitude. So, in the equatorial coordinate system, you can see the north celestial pole and vernal equinox, right ascension and declination. In alt azimuth coordinate system, altitude and azimuth are the two coordinates used to locate the position of a star. In this equatorial coordinate system, This right ascension and declination are the coordinates used to locate the position of a star. Now, by direct analogy, lines of latitude becomes lines of declination. Here you can see this is the declination. These are all the lines of latitude. Now, this declination is measured in degrees and this declination indicates how far north or how far south of a celestial equator the celestial object is. So, if you are locating a celestial object somewhere here, how far north it is from the celestial equator. Suppose you have a celestial object here, how far south the celestial object is from the celestial equator. This is what this declination denotes. Then lines of longitude have their equivalent in lines of right ascension. So, but whereas longitude is measured in degrees, minutes and seconds, east the Greenwich meridian, right ascension is measured in hours, minutes and seconds, east from where the celestial equator intersects the ecliptic. So, in this figure you can see the meridian, these are all meridian. This meridian is used to measure the right ascension of an object. Here right ascension is measured in hours, minutes and seconds east from where the celestial equator intersects the ellipse. So, this is the east. From east how far the object is, celestial object is. This is what right ascension measures. So, in equatorial coordinate system we are in need of declination and right ascension to locate the position of an object. Next comes ecliptic coordinate system. This ecliptic coordinate system use an eclipse. Here ecliptic is nothing but the plane of the Earth's orbit. The plane of the Earth's orbit is ecliptic plane here. This ecliptic plane is used by the astronomer by the movement of the sun. We are all know that sun is not moving, but according to the astronomers, sun is moving along with its planets in one direction. To track the path of the sun, astronomers have created an imaginary line that extends from the earth through the sun. You can look at the line. This is the line that extends through the sun, which indicates the movement of sun. So, during the year this line points to each constellation in the zodiac. Here you can see different constellations of star. So, through a year this line points to a zodiac. So, that is what this thing says. Next, the ecliptic coordinate system uses the ecliptic for its fundamental plane. As I told earlier, ecliptic is nothing but the equatorial plane of the Earth's orbit. Ecliptic is the path that sun appears to follow across the sky over the course of a year. This is what the equatorial ecliptic coordinate system says. Now, looking at this figure, you can see the celestial equator. The blue line is the celestial equator. This is that ecliptic. As I told, ecliptic is the plane of the Earth's orbit or movement of the sun. The intersection of this celestial equator and ecliptic is vernal equinox. Then the 0 degree longitude, north ecliptic pole and south ecliptic pole, this is the latitude. So, in this ecliptic coordinate system, ecliptic latitude and ecliptic longitude are the coordinates used to locate the position of a celestial object. So, it is also the projection of Earth's orbital plane onto the celestial sphere. Earth's orbital plane in the sense the plane of Earth's orbit. The latitudinal angle is called ecliptic latitude and the longitudinal angle is called ecliptic longitude. Like right ascension in the equatorial coordinate system, the 0 point of the ecliptic longitude is the vernal equinox. So here you can see the vernal equinox. This is the 0 point or origin of this ecliptic coordinate system. With respect to this origin, all other celestial objects or any celestial objects to be located shall be measured. Next, galactic coordinate system. The galactic coordinate system locates objects within the Milky Way galaxy by latitude and longitude in a similar manner to right ascension and declination in the equatorial coordinate system. Galactic coordinate systems are used to measure the movement of galaxies in our universe. Universe is made up of innumerable galaxies. So far, millions of galaxies are listed by the astronomers. What is the position of these millions of galaxies? That is, the galactic coordinate system explains. The current definition of the galactic coordinate system was finalized by International Astronomical Union in the year 1959. The galactic plane or the galactic equator is similar to the celestial equator of the equatorial coordinate system. It is a great circle of the celestial sphere made by the plane of the disk of our galaxy. In this figure, you can see the galaxy. This is the galactic center. The plane of that galaxy is the galactic plane. This is the star. The star position can be represented by the galactic coordinates, galactic latitude and longitude. So, the system defines a sphere enclosing the galaxy with the sun at its center, onto which galactic latitude, here I used B, and longitude L are projected. Galactic latitude ranges from minus 92 degree plus 92 degree below and above the galactic plane. The galactic longitude of an object is the angular distance around the galactic equator from the galactic center. So, galactic coordinate systems are used to find the position of an object in the galaxy. So, in this lecture we have seen the distances used in astronomy: light year, one astronomical unit, parsec. Light year is the distance travelled by light in 1 year. Astronomical unit is the average distance between sun and the earth. The more precise measurement of astronomical unit is equal to approximately 149 million kilometer. Then 1 parsec is the distance to a star that subtends an angle of 1 arc second at an arc length of 1 astronomical unit. We learnt that 1 astronomical unit is lesser than 1 light year, then 1 parsec. Then coordinate systems we have seen 4 coordinate system: alt-azimuth coordinate system, equatorial coordinate system, ecliptic coordinate system and galactic coordinate system. This is how measurements in astronomy can be learnt. These are the websites you can refer to learn more about the measurements in astronomy. Thank you.